the blackboard to lemmas from the previous talks that we are going to use. And I want to prove the theorem of isotriviality. So recall definition. So our base scheme S, which is assumed to be locally noetherian, is said to be geometrically unibranch if the normalization map so first we take the reduced scheme, and so it has a normalization still. So we require that this map is radical, which means adjective and say the extension of residue fields are radical. And a consequence of this, so this implies that the important fact is that the connected components of S are irreducible. This is the fact that is going to be used in the proof. And so this is also preserved by etale maps. So that is if we have a morphism P2S, which is etale, then P is locally noetherian. And also geometrically unibranch. Okay, so let's prove now the following proposition. So let S be locally geometrically unibranch. And let's consider a scheme P over S be quasi isotrivial constant scale over S. Then every connected component of P is finite. So this is a statement that every connected component is finite. So this follows easily from the previous lemma, because so since S is locally noetherian and geometrically so each connected component C of S is open, closed. And so replacing S by one component, one such C, we may assume S connected. And since we assumed that S was geometrically unibranch, then S is irreducible. And so let us denote by eta its generic point. Okay. And now let's C be a connected component of P. And as I said, P is still locally noetherian and geometrically unibranch. So C is open and closed, but and also irreducible. And so let's CB its generic point. And so we have our map P. So P is etale, and it's flat. And so for the generic point psi lies above the generic point below. And since C, since this is a generic point, so C is the closure of psi. And so for we look at the set of those points in C which projects onto eta. So this is the closure. This is the closure of psi in the fiber. But P is etale, and hence the fiber is discrete. Hence, so this closure is just psi itself. Hence, now we can apply the previous lemma with C equal to Z. So the connected component is open and closed. Hence, C is open and closed in P, and the fiber lying above the generic point consists just of one point, is finite. Hence, by the lemma, C is finite over this. So this proves this proposition. And now we can prove the following theorem. So again, S is assumed to be locally noetherian and geometrically unibranch. And let H multiplicative S group of multiplicative type over S of type a finitely generated abelian group M, which is assumed to equal the size of 3D. then in fact, then already is isofrequent. So, which means that it is split by finite etale extension that we are going to construct explicitly. And for the proof, is as follows. So we introduce these the diagonalizable group of the same type, M. Ah, 11.5. Yeah, sorry, I forgot. 11.5. Okay. And we are going to consider two functors. So how do I want to call them? Let us call E the functor of homomorphism of F group schemes from G into H. And I, like isomorphism, the functor of isomorphism of F groups between G and H. So these are just functors for the moment. But we made the hypothesis that H is quasi-isoperiodic. So this means that there exists a map S prime to S etale such that H lifted to S prime is isomorphic with this diagonalizable group M prime. And since M is finitely generated, we know that so E of S prime, so by so by base change, it is just the same thing of G S prime H prime. So this is form so over S prime, both are the same nice diagonalizable groups. And since M is finitely generated, we have this equality here. Let me write it like this. So we have this for formal reason. And since M is finitely generated, E S prime is represented by the constant scheme so we just take the endomorphism of M as the enclosed, and this is constant schemes of S prime corresponding to this set. Okay, because the hypothesis finitely generated was just to say that the home between these groups comes from the homomorphism of abelian groups between and then we see, and hence IS prime is represented by the constant, the constant the sub-constant scheme corresponding to the automorphism of M. Okay. Okay, and So now we are going to use this lemma here. So our map is etale, and it is faithfully flat, locally orthogonal representation. So we have twisted the constant scheme over S prime. So they are etale, and so they descend. Okay, so by lemma 823, the original functor E and I are represented by twisted constants over S. So actually now I'm no longer interested in E, so I'm just interested in I. So I is represented by a twisting constant scheme. So let us call it P, like in the previous proposition. And now let's see be a connected component of P. So it is etale over so it is, first of all, it is open. So it's an open open and closed, because in particular P is etale over S. So P is locally it is open and closed, and so the map C to S is etale, because it's an open in some etale, and it's also finite and finite by the previous proposition. 11, 11.1. Yeah. Okay. So being etale, it's open. Being finite, it's closed. And say C is open and closed in S. And still, since S was connected, so the projection is S. Okay, so and now we are done, because further the diagonal map E goes to C plus C. So this gives a section, over C of P, pc. Okay, so we have P, which is over S. So we take C, which is inside P, so we have this, and so now, so if we base change, so we have P plus C, and we have this. Yeah, yeah. Oh, yes, yes, yes. I was assuming, yeah, the same. So I should have said, yeah. So, yeah. So we can assume we can assume S connected, you're right. Because the connected components are open and closed, so the assertion is local, so it suffices to work over connected components. Okay, so we have a section which is just as a diagonal map and composed by the immersion of C into P. So this is a section of PC, but what is PC? So so this is a C point of PC. So this is an element. So this is an element of isomorphism of S group of GC and HC. So we have an element there, and HC is isomorphic to GC, which is the HC. And H is split by the which is, as we have seen, etale subjective. Okay, so this proves the theorem. Yep. Yeah. Yeah, it's a section of, so we base change to see. So here we may not have a section, but here we have a section which is the composition. Yeah, C cross C sits inside this one because C is an open subset of P. And so we have the diagonal map. And so this is a section of the projection because so the composition is basically the first projection here. And so the diagonal map is indeed a section of the set. And so we have a section, and so this section tau, so this is a point of our and P represents a functor isomorphism of S group of GS into. So this is a point of this functor over C, and by definition, the C point is a set of isomorphism over C of GC HT. So the section does provide an isomorphism between our two groups. And so this is a very nice argument that is going to be used further in the sequel to prove that reductive groups possess some properties where one can, well, or become isomorphic in over some etale extension. One considers the functor of isomorphism and prove that it is representable by a scheme which is smooth over the base, and a smooth scheme as section of a etale extension, and we had that. So this is a very nice argument that, yes? To descend, because so these are just functors. It's not clear that they are schemes. But if we pull back to S prime, this functor, now that we have replaced the unknown group H prime, HS prime by this known group, Now we know that we have proved earlier that this functor is representable by this group, this scheme. And then clearly the subfunctor of automorphism is represented by this one. And so this one is, so this is a locally constant. So the map to S prime is etale. And we also have made a base change, which is etale. And now we use this lemma to ensure that the functor is already represented over S by some scale. And so we need this because this need not be affine. So we cannot use the most usual criterion of descent, which is that if we know that the scheme here is affine, then it descends. But then it's, well, it's not affine if this automorphism group is infinite, but it is etale, and so we use 823 instead. Okay. Okay, so we have proved our theorem, and now I can conclude with some well, come back to Galois theory. So let me mention briefly a brief section about classification of isoprivileged. Groups. So here we assume that the base scheme S is connected. And recall so type of range S prime to S is so what type of range means is a subjective etale finite. And then then for the direct image is locally free OS module of some rank n, which is the degree of S prime over S. So if we denote by gamma the automorphism group, so the automorphism of S prime, which induce the the automorphism of S prime over S, so it is finite. And its cardinality is not more than n. And one say that S prime over S is the Galois ring, or the Galois ring. If S prime is connected, and the cardinality of gamma is exactly equal to n. Okay, so if S is the spectrum of the field, so this corresponds to a Galois extension of field. And so what do I want to say? And so the following facts are known. So firstly, if S prime if S prime to S is an etale covering, S prime has finitely many connected components, many connected components, and uh, each of course, open and closed. C. And each map C to S is still an etale covering. Okay, so if we have an etale covering, we can always restrict to a connected one. And I'm not sure. Yeah, because it's and so the second point is that if for every etale covering S1 to S with S1 connected is dominated by some error covering. Okay, so this means that we start with S, so we take any well, we have this S1, so there exists S prime, which is over S1, and so this one is a Galois. Okay, so these are just one known result about Galois theory. And so now we, so now if, so let's H be an isotrivial multiplicatively M-type group over S, then there exists S prime to S etale such that H S prime is diagonalizable. And so by 1 and 2, we can assume S prime to S equal 1 with group gamma. Because so since this is split over S prime, so it remains split over any connected component, and then we can live to a Galois cover, and so we have done. And now we are basically in a case that I mentioned before. So let me just give without proof the following theorem. Oh, this is theorem 12.3. Let's S be connected. And S prime to S, Galois cover. Galois of ring with group gamma. Okay, then the category letters denoted by empty S prime over S of empty groups over S which split over S prime, that is, which become diagonalizable over S prime, is anti-equivalent to the category of finite derivative. So this is just abelian groups and with a linear linear action. Okay, so the correspondence in one direction is that if we have such M, so we associate, so we take the group algebra of M over S prime, and we take the gamma invariance, and in the other direction, if we have an H, so we associate to it the character group D of H, so which is a twisted constant, twisted constant group. And sorry, and if we lift it to H prime, so this becomes a trivial group, and by descent, and well, by Galois descent, and D of H corresponds to some action of gamma on M. Okay, and so if the action is trivial, then the descended this is MS itself. Okay, so okay, I don't want to spend more time on this. But so we have, so this way we have a complete description of well, of multiplicative type group which splits over some finite extension. And just to be complete, let me finish this part with the following proposition. 6. Let K be a field that I finitely generated abelian group. Then any multiplicative group of multiplicative type over the spectrum of our field of type n is either trivial, that is, it fits over a finite separable extension. Okay, from okay, just a very brief sketch of proof by general reason, general reason. H splits over a finite extension. K of K, not necessarily separable. And we consider that K prime is a separable closure of K. And so we have the following picture. So here we have spec K going over spec K prime going to spec K. And here we have a locally constant group, which is a character group of H. So it is a twisted constant group. In particular, it is etale. And so we take the pullback here. So it is also etale. And we take the pullback here. But by assumption, this one is split. So this is a constant. Here, this is a constant scale. Okay. Now we can apply a general argument, and so this map here is purely inseparable. Okay. And now I can use a general fact that an inseparable extension induces an equivalence as a category of etale schemes over the base. So any etale scheme here comes uniquely from an etale scheme here. And this one goes to this one, which is split, and so this one is already split. So this is, okay, so this is the argument. Okay, well, so I wrote a self-contained proof in my note, because in the case of a field extension, this can be done by hand. But the general statement is this, that a radical morphism of scheme induces an equivalence of the category of etale schemes over the given basis. Okay, so in the remaining time, I want to start talking about the beauty of expose 3, which is lifting, infinitesimal lifting of homomorphism. Okay. And yeah, it's the exposé by the mesure. So so the next, so I start, so infinitesimal liftings. And field homology. And I add a subtitle, which is the beauty of SGA 3 exposés. Because there are some really beautiful ideas. Somehow they are buried into, well, they are buried into two general statements, and well, it's rather daunting when you look at it, but well, if you extract just a little part of it that is needed for the sequel, it's really beautiful. Okay, so let us start section 13, which is motivation. And so the motivation is the study of tori in reductive group space. Okay, so let's start with the definition. So definition. So a group scheme G over the base S is called reductive if two conditions are satisfied. So firstly, G is smooth and affine over S. And secondly, every well, so I can define at the same time reductive or semi-simple, respectively semi-simple. If, well, a smooth and affine, and for any point S in S, and I denote as usual by S bar the spectrum of an algebraic closure of the residue field of S. The requirement is that the geometric fiber G of S bar is reductive, effectively semi-simple. Oops, I forgot an important hypothesis with connected fibers. Okay, so, or if you like, in the definition of reductive or semi-simple group of a field, and a very closed field, we insist that the group is connected. We do not want component groups. Okay, so this is a very weak definition because we only require that it's smooth and affine with connected fibers, but then there is a requirement only on the fibers. And another the next definition is, so let G be reductive group scheme of S. So what one calls a maximal torus. Torus T of G is a sub scheme such that, so firstly, T is a multiplicative group of type ZD for some D. So this is so this means that T is a torus. And secondly, for any geometric point S as before, T S bar is a maximal torus. Hmm? Well, yeah, you're right. Maybe I should. Yeah, probably I should add those. Okay. And so the goal is to prove that maximal tori exists etale locally. So it means that for any S in S, there exists an open neighborhood U of S, and U prime to U etale, such that G U prime contains maximal torus G U prime. So I pause here to say that this is a highly non-trivial. This is a highly non-trivial results, because just look at the special case where so included in the definition of reductive, you could take a group which is smooth and affine with connected fibers, and all fibers are tori of the same dimension. And then so it's weaker than the previous definition of a group of multiplicative type, because a multiplicative type, we want the group to become trivial over some given etale neighborhood. And so the result is that actually the fiber-wise property suffices to, so if you apply this to the case where G is fiber-wise a torus, so actually the TU prime will be equal to that one. And so this means in particular that this group is of multiplicative type. And so this also proves that any group of multiplicative type over any base is quasi-isotrivial. So I wished I could escape the proof of this result, which is difficult, but actually I cannot, because basically the proof the proof of this will include the proof that any group of multiplicative type is isotrivial. Yeah, yeah. And Yeah, so the definition is weaker than for groups of multiplicative type because well, we look only at the fibers. And so let me insist that yeah, and so let me insist in this respect so that the assumption with connected fibers is important because so just a remark. So the assumption connected fibers is really important because just take an algebraically closed field, say of characteristic different from 2. Let S be the affine line of a K. And consider the constant group, with 2 elements over S. And so it is a multiplicative group, actually. And let H be the open subgroup obtained by removing the point, the non-neutral point, that is let's say the non-neutral -1 over the point over S equal to 0. So we have the affine line is here the 0. So you take the constant group plus or minus 1, and you just remove this point here. So this is your group scheme H. So H is etale affine over S. Fibers are as the unit group or plus or minus 1. So they are the fibers are diagonalizable groups, but H is not a group of multiplicative type because in the neighborhood of in any neighborhood, even at base change, this will not be a group of multiplicative type because the type of the fibers is different. So for the 0, you have just 1 point and over. Okay, so this is the reason why one should insist that the fibers are connected. Okay, so I mentioned, however, that there is a result of Grothendieck, which says that if we impose that the fibers are all the same, then it is indeed indeed a group of multiplicative type. But just to play, so just to be safe, it's important to assume connected fibers, so we don't have a problem like that. Okay, so let me start with so, well, I start with the definition and I explain it later. So one says that a contravariant functor F from the category of schemes, the category of sets, is called formally smooth. If for every important ideal I in a ring A, the map, so the map from spec A to spec of A over I is projected. Okay. Okay, so, well, I will comment later. And so the remark, so this is connected to the, related to the usual notion of smoothness. If F is represented, okay, so let's say that we work with a category of scheme of a fixed base. So if F is represented by S scheme X, and if X is locally of finite presentation of S, then X is smooth. Okay. Is that correct? Or do I need a flatness hypothesis? No, it's contained already in the, okay. So to prove smoothness of a scheme, well, we have to know first that it has to be a scheme. You need some finiteness hypothesis, like locally a finite presentation. And then you have to check for smoothness. Here the process is somehow reversed. So we are going with functors that ultimately will be proved to be scheme. But first one proves that they are formally smooth. And just from formal smoothness, one can already deduce some interesting consequences. So we start with the notion of formal smoothness for a functor, and this is already quite useful. Okay, so to which functors do we want to apply this? So let me, so what was the motivation? So section, so this one is really about infinitesimal liftings. So just a piece of notation, definition. Consider a morphic F prime to S. And it's the prime F prime T. Then one define a functor pi of F prime over S of F prime by the property. So this is a functor on S schemes by the property that so it's T point. So this is just so these are just the T point. So these are So these are the okay. Well, no. Let us keep it like this, because so the special case, so X is S scheme. So we can lift it, we can base change it to it, and then for any scheme T over S, the restriction of scalars of X plus S squared S prime of T. So this is the homomorphism of S prime schemes of T plus S F prime into X plus S F prime. So this is just from S T plus S F prime X. And so these are just these are just the points of X with value then this. Okay, so this is just a notation. So, well, for example, if you have a scheme over C, you can consider it as a scheme over R, and so this is a restriction of scalar. Okay, and now let us start with our notation. I just want to introduce the setting, and so the computations will come in the next lecture. So from now on, notation. So lambda will be a ring, and I contain G will be nilpotent ideals such that the product Ig is equal to 0. So in particular, J square is 0. And so this think of a given nilpotent ideal, and J is equal to IF, because we are going to make, we want to prove things for an arbitrarily nilpotent ideal of index of nilpotence n plus 1, and we are going to proceed by induction, and so we will need this J, which is this one. Okay, so this will be for inductive arguments. Okay, so for these reasons, we have the two letters I and J. And S will be the spectrum of lambda. So it contains Sj, which is a spectrum of lambda over J, and it contains Si, which we also denote by S0, which is they all have same topological space. Okay, and we want to lift objects living over here, over S0 to object over S. And so this is called infinitesimal lifting because, well, the topological is the space, the topological space is the same. So they only differ by nilpotent elements. Okay, and now the definition, and also fixed. So let G be an affine smooth group, uh, group S group scheme. So this would be our standing assumption for the rest of this lecture and the next one. So we have a fine smooth group scheme, so given by, so A is a lambda algebra. Lambda is a ring corresponding to our base scheme. And we are going to come slowly to the Lie algebra of G. And first, the definition denotes by G plus so let me write first the frightening definition, and then I explain it in words. For the restriction of scalar of G base change to this. So this is just a notation to mean that that is for every S scheme Y, an element of G plus of Y is a morphism of SG schemes. YJ so let's cut it back here into G. Okay, and of course this one sits inside actually, and so so we are so Y is a S scheme, so we obtain Yj by base change to this one, and so what we are giving here is a map, and the main question is, can we so can we find okay, can this map can be lifted to the whole of Y? Okay, so this will be the setting, and so clearly T plus is a group functor. Well, because G is a group, so 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 actually we are so these are actually the G as J point of Y as J. So this is a group. Okay, so this is a group functor. And we are going to study the obstruction to lift a morphism like this. We are going to study in which situation we can find a dotted arrow. Okay, so let me start with an example. An easy example. Let's take a ring. It can be an algebraic closed field if you want. Closed field if one wants. And let G, the group scheme GLN, the GLN of a spectate. So we know that the Lie algebra of G is the K module, the free K module of the matrices of size. And so as K module, so this is a free K module of rank K to the n squared. And so we define a functor, define the functor W of Lie of G from the category of K algebras to the category of Y sets, if one wants. And it sends, well, so the value on algebra, so this is just this K module Lie of G tensor over K with SAS. That's a very easy functor. Now let's epsilon be an indeterminate such that a square zero indeterminates. And I claim, so we have an exact sequence. We have an exact sequence of group functors. Well, that you all know. So we have this W of E of G that goes into the restriction of scalar from K epsilon into K of G. And there is a natural map here to G. Well, so this is just a very pendant, right? So this is a very pedantic way to write the following facts. Okay, so we are going to, so this means for any K algebra R, we have exact sequence of groups. Oh, I forgot to introduce a notation. So we have the algebra map from K epsilon to K, which I denote by pi. So which send epsilon to 0. Okay. And so we have our group GLN with value in the ring R epsilon. So we have the evaluation map sending epsilon to 0. So this goes into our GLN of R. And what is the kernel? Well, the kernel is naturally isomorphic with an ender R. So let me, okay, so let me put one here because there's a group. So this just means that's okay. Okay, so the point here is twofold. I gave this example because I want to. So the first point is that the addition flow on Mn of k coming from its k module structure is the same as the one coming from G well through this exact sequence. So this means when I consider this as the kernel of pi coming from, okay, through, so this means, so through this identification. And the second point is that the adjoint action of GNN on its Lie algebra, that is a space of k by k matrices, coincide with the action by conjugation in GNN of epsilon. Okay, so both these points are easy because so let us denote by H the kernel of this map. And R points of H is a matrix of the form, it's the identity matrix plus epsilon A with a non square matrix. And of course, if we multiply two of those, we find this. Okay, so the group law induced as kernel is indeed the usual addition of matrices. And secondly, if for any matrix B invertible in GLN of R, so B times Rn plus epsilon A B inverse. So this is Rn plus epsilon B B inverse. Okay, so the conjugate, well, so if we identify n by n matrices with the kernel of this group morphism, well, it's a normal subgroup, and the action by conjugation is the adjoint action. Okay, so you all knew this, and this is But it's good to start with this because we are in the next lecture we are going to play the same game, but here it will be G and here it will be G plus, and the Lie algebra here will be replaced by something very similar but slightly different. Okay, so the formalism is may look daunting, but actually the ideas are very simple, and it's really very analogous to this situation. Okay, so this is a non-trivial point that is proved in SGA3, exposit 2. It's a bit tricky in general, but it's true, and so you knew it already in the case of GLM. Okay, so I will stop here, and next lecture we'll continue with this formalism. Yes, because one uses V for vector bundle. No, this is not precisely. It's the other one. So if one has a module L, so one has this functor is representable because it's a symmetric algebra. Okay, so if L is locally free. No, okay. So for any module L, we can define this, and if L is locally free, oh no, in any case, okay, so V is a good one that is always representable. Yeah, it's a spectrum of this. Okay. So it's the spectrum of this. Okay, so this is a vector bundle whose fiber correspond to the dual module L star. And so in this and W of a module is it's a naive definition that one just takes this. So in general, it's not representable. But if the module here is locally free, which is the case when our group is smooth, then actually it is. No, that's a good question because we are going to use this intensively. So actually, it's a vector bundle corresponding to the. Okay, because actually the primary object has a relative differentials. Okay, and the Lie algebra is only defined as a dual of that one. So this is the true interesting object, but since everybody is more familiar with the Lie algebra, I started with that. But under our good hypothesis, so this guy is this guy. Okay, so this is a whole story. Okay, so we continue with Lie algebra and deformation next Tuesday.